Morning class. It's time for us to start. So I'm going to go ahead and I just want to write down some of the things I want to talk about today because last class I kind of went over that in a hurry. So let me write down here, and I think these are some of the concepts that once we understand the differences between these concepts, the first one, is called the electric potential. I'll say that we calculate this at a point. And then the second one is called the electric difference. Between point A and point B. So that's for the electric potential difference. So let me just kind of. So this is V. So the symbol here is V, and then the symbol here is going to be VAB. Now VAB is just VB minus VA. So you can see that the potential difference. So if you've calculated the potential at a point, right? Then when you calculate the potential difference between 2 points, you just take the potential at 1 point and then you subtract that from the potential. So this is going to make more sense. Again, later on, if you think about like a body here, and we say that this is plus and this is minus, and we say this body is 12 volts, then it means that the potential difference between this point, call this point B and call this point A. So it means that there is a 12.0 volt potential difference between point B and point A. Right. Now there is so many ways that you can look at this. For example, you can say that, just as an example, you can say that, for example, point B is at 6 volt and point A is at -6, right? So if 6 and -6, that's going to give me a difference of 12. Or sometimes you can also say that point B is at 12 and point A is at 0. Then if you take the difference between 12 and 0, you still get the same value, right? Now the third quantity that we're going to look at here is called the electric potential energy. The symbol here is U subscript E. And you're going to say that U subscript E is test charge times VAB. As I said last class, VAB is going to be joule per coulomb, right? So if you take joule per coulomb and you multiply by coulomb, you get something that is an energy. So electric potential energy is something that is going to be in joules. And then finally we have electric work. And in the notes, this is given by WE. We just call it internal energy. It's the negative value of the electric potential energy. Now again, and let me explain why we put a negative sign, right? So the reason why we put a negative sign is because if you remember from PSE1, if I take an object and drop it from some height, right, then we're going to say that as it moves from this point to the floor, potential energy gets converted into kinetic energy, right? So if this object is moving down, it's losing potential energy, but gaining kinetic energy. I don't know if you guys remember this from PSE1. So you take an object at some height, you let it drop, it's losing potential energy, but gaining kinetic energy, right? So going down means it's going downhill, it's losing potential energy. So similarly, when we solve a problem for electric potentials, when we go from a high potential to a low potential, we're going to say that the system is losing energy, right? So it's losing potential energy, but gaining kinetic energy. Now with this, now keep this in mind, and then let's go back to the problem that we were solving last week. So keep all of this in mind. So you have potential at a point, you have potential difference between 2 points, you have electric potential energy, which is in joules, and then you have the work. So let's go back and look at the problem that was not solved in last class. So let me open this. So this is the file. So if you remember, we derived this equation last class on how to calculate the potential at a point. And then we calculated the potential at 2 points. So if you look at how we calculated this, for example, you have the potential at point A, which is just given by KE, is KE times Q over XA, which if you substitute everything here, you get 3.60 times 10 to the power 6 joules per coulomb. That's the potential that we calculated at point A. Now, if you do the same thing and substitute everything and calculate the potential at point B, you get 1.80 times 10 to the power 6 joule per coulomb, right? And then we also calculate the potential difference between point A and point B, which is given by this equation right here. So it's just the potential at point B minus the potential at point A. So we ended up getting a negative value here. And I said that this negative value simply means that there is a decrease in the potential energy. All right. So now let's go ahead and calculate. So let me open a new. So this is the problem that we're solving. You have a positive charge, it generates these electric fields. And then we said that if this is my point A and this is my point B. So what we've seen so far is that we've calculated so we have our potential at point A was 3.60 times 10 to the power 6 joules per coulomb. Calculate potential at point B. This was 1.80 times 10 to the power 6 joules. Now, with this, you can calculate VAB, which is just equals to VB minus VA. And this gave me negative 1.80 times 10 to the power 6 joule per coulomb. So now let's calculate the electric potential energy, UE. So suppose that, so let's put a positive charge here. This is my test charge. So remember that this is fixed. This is the source. What does an electric field do to a positive charge? It repels it, right? So it pushes. So when you push something, you're giving it energy. So push is work, is energy. So I can calculate, so let's say that this test charge is Q, I'll just call it 1.0 coulombs. So it means that my electric energy here is Q times VAB. So this value is going to be equals to negative 1.0 times 10 to the power 6 joules. And then I can calculate the work. So work. So this So this is just called internal energy. Then this is negative UE, which is 1.80. Now suppose that this test charge has a mass of, let's just say, 0.1 kilograms. Yeah, go ahead.
On the UE, or for the electric potential energy,
Yes.
wouldn't the 1.8 times, well, the negative 1.8 times 10 to the 6 be multiplied by the 4 microcoulombs? Like the test charge from the problem we're basing it off of?
So the test charge here is 1.0. Remember the source was 4.0, right? It was 4.0 microcoulombs.
No.
This was the source, and this is the test. And this is 1.0 coulombs. It's not 1.0 microcoulombs. It's just 1.0 coulombs. So VA was 3.60 times 10 to the power 6. Is that correct? From last class?
Thanks.
Yeah. Now, so again, if we say that this test charge has a mass of 0.1 kilograms, and then let's suppose that we put it at rest at point A, can you calculate? So let's take the velocity at point A to be 0. Can I calculate what the velocity at point B is going to be? So to solve this, I'm just going to say that all of this energy here gets converted into kinetic energy, 1/2 times mass times the velocity at point B squared minus the velocity at point A squared. Now, so just something that I just want to make sure that it's a little bit, so for velocity here, I'm using the lowercase, so I'm using lowercase v, just so that we don't confuse this with the potential difference. So potential difference was uppercase v, velocity is lowercase v. Now solving this, I can get my velocity at point B using this equation here. So velocity at point B is going to be 2 times 1.80 times 10 to the power 6. And then we divide this by the mass, which is 0.1, and then we take the square root, all of that. And so that should give me so that should give me 6. Just a second. So basically, what this problem is telling me is that when you put a test charge here, as the test charge is going to pick up speed, This is picking up speed because the fixed charge is pushing. So the electric field is pushing that particle. And when there is a force acting on the particle, on the charge, we give it energy, and this energy is going to show up as an increase in the kinetic energy.